Welcome to the deep dive.
Great to be here.
Today we're tackling ANOVA,
Yeah.
Analysis of Variance.
Yeah.
We've got a bunch of questions people often ask about it.
And the goal.
Our mission really is to just cut through the jargon, give you a clear picture of what ANOVA is, why it's used, without, getting bogged down in formulas.
Sounds good. Making it accessible.
Exactly. So let's jump right in. The big question first. Why ANOVA? Why do we need it?
Well, basically you use ANOVA when you want to compare the average results, the means of more than two groups.
Okay, more than two. So not just comparing A and B.
Right. If you only have two groups, a standard t-test works fine. But imagine you have 3 or 4 or 5 groups.
Like different teaching methods, maybe?
Perfect example. If you start running t-tests between every single pair method, 1 versus 2, 1 versus 3, 2 versus 3, your chance of getting a false positive, thinking there's a difference when there isn't, it actually goes up quite a bit.
Ah, right. The multiple comparisons problem.
Precisely. ANOVA gives you one single test. It tells you if there's any significant difference somewhere among all those group means overall.
So it's more efficient, statistically safer for multiple groups? Makes sense. But for the results to be trustworthy, are there conditions, assumptions?
Yes, there are a few key ones. We don't need to dive super deep into checking them now, but basically...
The main ideas.
Yeah. First, the observations in each group should be independent, like one student's score shouldn't influence another's.
Okay.
Second, the data within each group should be roughly normally distributed, bell curve shaped, more or less.
Right.
And third, the variances, the spread of the data should be pretty similar across all the groups you're comparing. We call that homogeneity of variances.
Okay. Independence, normality, equal variances. Got it. Now, the F statistic. That seems central to ANOVA. What is it telling us?
Think of it kind of like a signal-to-noise ratio.
Signal-to-noise.
Yeah. It compares the variability between the group averages, that's your potential signal, the effect of your factor.
Like the difference caused by the teaching methods.
Exactly. It compares that to the variability within each group that's like the random noise or natural variation you'd expect.
So a bigger F means?
A bigger F statistic suggests the differences between the groups are large compared to the random variation within them. It means it's more likely that the factor you're studying actually has an effect.
Okay, that's clearer. Bigger F, more likely a real difference. How does ANOVA actually calculate this? You mentioned variability.
Right. ANOVA works by partitioning the total variation in your data. It breaks it down.
Breaks it down how?
It takes all the variation you see across all your data points and separates it into two main pieces.
Okay.
One piece is the variation between the group means. This is the part potentially explained by your factor.
The signal part again.
Right. And the other piece is the variation within the groups. This is often called the error or residual variation, the unexplained noise.
So it isolates the effect from the noise.
That's the core idea, yes. By comparing these sources of variation, we get the F statistic.
Cool. Now I hear about one-way and two-way ANOVA. What's the difference there?
It's pretty straightforward, actually. It just depends on how many independent variables or factors you're investigating.
Factors being the things you think might cause a difference.
Exactly. A one-way ANOVA looks at the effect of one factor on your outcome variable, like our teaching method example, just one factor.
Okay, one factor, one way. Easy enough.
A two-way ANOVA looks at two factors simultaneously. Maybe you want to see the effective teaching method and the amount of homework students do on their test scores.
Ah, so two things at once.
Yes. And importantly, two-way ANOVA also lets you look at whether those two factors interact.
Interact, what does that mean?
An interaction means the effect of one factor depends on the level of the other factor.
Can you give an example?
Sure. Maybe teaching method A is super effective, but only if students also do a lot of homework. Method B might be okay regardless of homework load.
So the effective teaching method isn't consistent across different homework levels.
Exactly. That's an interaction. Two-way ANOVA can uncover those more complex, nuanced relationships. A significant interaction term tells you this is happening.
That's powerful.
Yeah.
Okay, so let's say our ANOVA one-way or two-way gives us a significant result. It says there's a difference somewhere.
Right. The overall F test is significant.
But how do we know which specific groups are different? If
Yeah.
we have 3 teaching methods, is one different from 2? Or 1 from 3? Or both?
Great question. That's where post hoc tests come in.
Post hoc, meaning after this.
Exactly. After you find a significant overall ANOVA result, you run post hoc tests, like Tukey's HSD is a common one. These tests perform pairwise comparisons.
Comparing each group mean against every other group mean.
Yes. They tell you specifically which pairs of groups have statistically significant differences between their means while controlling that overall error rate we talked about earlier.
Okay, so ANOVA says there's a difference. Post hoc tests that say here's where the differences are.
You got it.
Last one, repeated measures ANOVA. What makes that special?
Ugh, repeated measures. You use this when you measure the same subjects or items multiple times.
Like tracking patient symptoms over several weeks, or maybe testing the same person under different conditions.
Exactly. Because you're measuring the same entity repeatedly, those measurements are likely correlated, right? Someone who starts with high symptoms might generally stay higher than someone who starts low.
Makes sense. My measurement at week 2 is related to my measurement at week 1.
Right. Standard ANOVA assumes independence, which isn't true here. Repeated measures ANOVA specifically accounts for that correlation within subjects.
And what's the benefit?
It often gives you more statistical power, a better chance of detecting a real effect if one exists, compared to trying to use a standard ANOVA design for this kind of data.
Got it. So it's tailored for that within subjects type of study.
Precisely.
Okay, let's wrap this up. Key takeaways. ANOVA is for comparing means of more than 2 groups. It analyzes variance using the F statistic as that signal-to-noise ratio.
Yep, partitioning variability into between and within groups.
We have one way for one factor, two way for 2 factors, plus their potential interaction.
And if ANOVA finds a difference, post hoc tests pinpoint where.
And repeated measures. ANOVA is the special tool for when you measure the same subjects multiple times.
That covers the main points, I think. It's a really flexible framework.
Definitely. So here's something to think about. As you go through your day, or look at data in your own field, notice when comparisons are being made across multiple groups.
Yeah, it happens everywhere.
How could the logic of ANOVA thinking about variance between groups versus within groups help you understand those situations better? What kind of factors might be driving the differences you see? What questions could you ask?
Interesting angle.
That's your thought for this deep dive. Thanks for joining us.
My pleasure.